So another example of circular motion that we like to look at is this problem of going around a bank curve. So you may not have realised it or not, but whenever you're going around corners on roads and whatever, there is a slight banking there to assist when you're driving along. So we're going to look at a little bit of detail. So the green triangle represents the bank of the curve. The red object, I guess, is Bob, and it makes an angle. So we'll put Bob in the middle of that there. So what are the forces acting on Bob? Well, we have a normal force. Whenever you make contact with a surface, you have a force going at right angles to the surface. And we have the force due to gravity. It's remarkably similar to the conical pendulum, actually. It's just that we've replaced tension with a normal force. But the reality is, it's sort of the same problem. So we end up with similar things. So horizontal forces, again, we're going around a corner or whatever we're doing, but we're in a horizontal circle. So they'll all sum to be mv squared on r, or mr omega squared if you're using angular velocity. And so there's good old Bob. We'll have a component. Now, working out where theta is for this one, got to play with geometry a bit, but using the knowledge of the normal force being perpendicular to the bank there, we can play around with alternate angles and what have you, angles in a triangle. Theta ends up being in that position there. So we'll have n sine theta going to the left, n sine theta. And so n sine theta is the resultant force, mv squared on r. Vertical forces, well, if you're going around the corner, we certainly hope the car doesn't lift off the track. So we want to have no vertical forces. So we have n cos theta going up and mg going down. And as I say, we get pretty much the same equations as we saw in the conical pendulum, which means we can do similar things. So tan theta would end up being v squared on rg, like we saw with the conical pendulum. Let's then do an example. A railway line has been constructed. Oh, how topical. And it's going to go around a circular curve of radius 400 metres. The distance between the two rails is 1.5 metres, and the outside rail is 0.08 metres above the inside rail. So we've got to find the most favourable speed that eliminates any sideways force on the wheels. See, in a car, it's not as big a problem. I mean, if you slide a little bit in the car, not a big deal when you're going around a corner. In a train, it's a big problem, because you don't want the train to derail. So they kind of need to know the speed that you need to take the different corners at. So again, let's draw up the diagram. So we're saying the distance between the tracks are 1.5 metres. So one track, if you like, is at the bottom of the bank. And the other one is 0.08 above the one at the bottom there. So our forces, we'll have our normal force, and we'll have our gravitational force. So let's solve our problem. Work out where theta is. Theta ends up being in that position. So horizontal forces, basically exactly the same as I did then, exactly the same as I did with conical pendulum, but it's how we approach all these problems. Draw up our force diagrams, have a look what's happening horizontally, have a look what's happening vertically. It should give us all the equations we need to solve our problems. So vertical forces, and there's our two familiar equations, n sine theta, mv squared on r, n cos theta, mg. Don't quote those, derive them each time. So tan theta is v squared on rg. That's going to be handy for this question. Now, I don't actually know tan theta, but I can work out sine theta from that triangle. Sine theta works out to be 4 and 75, and so from there I can work out tan theta. So it'll be 4 on the square root of 5,609. Okay, so v squared on 400 times 9.8 will be 4 on the square root of 5,609. We end up with, well, originally it's in metres per second, but obviously if you're driving a train or a car or whatever, kilometres per hour is probably a more useful measurement to have. So 52 kilometres per hour. Because there's another interesting force that happens, and that's friction. So this particular one comes from 1995, takes into account friction as well. So same sort of problem, the mass is going around the circular track, but we now have this frictional force. So the component F, due to friction. Now, it might go up the track, it might go down the track. It depends. Because it's a resistive force, so it depends what you're doing. Now, if we're going at the optimal speed and we're going around, it's fine. But if we were to slow down, then maybe we'll start falling down the track. And if we do that, there'd be friction going up the track. Or if we were to speed up, like we saw with our conical pendulum, it rises. Well, same sort of thing will happen here. If we speed up, we'll go up the track, which means friction will go down the track. So for our problem, they've said positive friction, negative friction. Well, one's when it's going up, one's when it's going down. And they've said positive is when it's going up the track. That'll be the positive friction. And friction is always some constant times the normal force. So mu is the constant they've decided to use for this problem. Acceleration due to gravity is g, just reminding us about the v squared on r, and so on. Okay, so what do they actually ask? By resolving the forces horizontally and vertically, show this wonderful expression here, which, you know, can look quite daunting, I suppose. You go, ugh. But do the same thing, which is resolve our forces. They've even told us resolve them horizontally and vertically. So let's have a look at what's happening. I need to draw some triangles for the normal force and the frictional force. Locate where theta would be. So we've got alternate angles, theta's there. That becomes 90 minus theta, so that one's theta. And then the other triangle got 90 minus theta, so the one at the top is theta in the friction triangle. So from there, we should be able to work it out. Horizontal circle, so yep, mv squared on r. Horizontally, we have a component of the normal force going to the left. The friction one will be going to the right because it's going up and then across to the right. They will sum to give mv squared on r. Remember, the positive direction is always towards the centre. So in our diagram, it's towards the left. So n sine theta minus f cos theta will be mv squared on r. There's the top of the fraction that we need. Okay, let's have a look at the vertical forces. We have a component of the normal force going up. The frictional force is also going up. Gravitational force is going down. They will all sum to give 0. And I get the bottom of the fraction now. N cos theta plus f sine theta is mg. Now, I did this a rather strange way. I don't know why I didn't just go, oh, well, it's going to be n cos theta. For some reason, I started with the left-hand side, which in hindsight was rather stupid. But anyway, v squared on rg would be mv squared on r times 1 on mg, which does get what we want. It probably would make more sense, as I say, to start with the right-hand side. But anyway, it doesn't really matter. However we end up with it. Okay, so now about this. We want to show the maximum speed that we can travel without slipping up the track. And we're going to call that V max. So V squared max will be tan theta plus mu. Oh, sorry, V squared max divided by Rg will be tan theta plus mu over 1 minus mu tan theta. And we're allowed to suppose that mu tan theta is less than 1. That was nice of them. What would that be? Ah, yes. You don't want the bottom to be a negative number, do we? Okay. So it's friction that's resisting the particle moving up or down the slope. We're saying it's not slipping up. So if it's not slipping up, friction must be a maximum in the opposite direction. Because it's resisting the movement up. Going down the plane, we said that was the negative. So friction is minus mu n. I can substitute that into what we just found then. So v squared max on rg will now be n sine theta plus mu n cos theta on n cos theta minus mu n sine theta. Well, the n's are going to cancel. I want tan, so if I divide everything by cos, and we'll get the expression that they're looking for. Okay. So I guess the key to that is realising that friction is negative mu n in this situation. The resistive force would be going down the track. Now, suppose that mu is greater than tan theta, or equals it, then the particle will not slide down the track regardless of its speed. So it doesn't matter how fast you're going, you'll always go up or stay stationary, but you will not go down. So now I'm trying to find the minimum speed, I suppose. So the minimum speed that can travel without sliding down. So this time we're trying to resist it going down, therefore the friction must be going up. So now the friction is maximum in the opposite direction, it's positive mu n, which basically means I'll get exactly the same formula, but the sign will be different on the mu. So V squared minimum on Rg will be tan theta minus mu on 1 plus mu tan theta. Now, we've been told that mu is greater than or equal to tan theta. So therefore, V squared minimum on Rg must be less than or equal to 0. Why must it be less than or equal to 0? Yeah, because the bottom's going to be positive no matter what. But the top, if I'm taking away something that's greater than tan theta, I've got to get a negative number. So V squared minimum is less than or equal to 0. Well, then it's got to be 0, because I can't square it and get a negative number unless my velocity is a complex number, but because I don't know too many things that travel at a complex number, meters per second. That would be interesting. Anyway, so the minimum velocity therefore is 0. So what we're saying is the minimum velocity for it to not slide down the track is 0. Well, it never slides down the track. Thus, minimum velocity is 0. It will not slide down regardless of the speed. All right. Oh, yes, this is a nice one. 1996 question. So imagine, I guess the easiest way to describe this is, imagine you've got a 40-gallon drum, something like that. So that's the cross-section there. And inside our 40-gallon drum, we've got a ball bearing or something like that. And so the ball bearing's on the inside, and we're going to rotate the drum, but the ball bearing is going to stay on the surface of the drum. So they've given us all the conditions there. The particle is rotating around the drum. Radius of the drums are meters, etc., etc., etc. What else do we need to know there? It's all pretty much standard, but you'll notice here, remember the ball bearing's inside the drum. So the normal force is going towards the centre. Now, how do I know it's going towards the centre? Other than they've drawn it on the picture for me. Remember, when we make contact with a surface, if it's a curved surface, I would assume it's the tangent. The tangent is perpendicular to the radius. But we also know the normal force is perpendicular to the surface, so it's going down the line of the radius. Must be going that way. Our frictional force would go along the bank, which in this case is the tangent. So it's going off in the direction of the tangent as we go along. We want to find an expression for F on n. See what I did? Beautiful thing about circles is they can be rotated. So whilst they've said, because normally I would say horizontal forces equal this, vertical forces equal that, but they want me to do it along the, there we go, resolving forces perpendicular and parallel to OP. So I'm just going to turn the picture so those two directions look horizontal and vertical. What it basically means though is now gravity is no longer a vertical force. I'll have a component of the gravitational force now. So let's put that in. And theta, again playing with the geometry, theta would be there. It also means my resultant force. Right? Resultant force in circular motion. What's going to happen? Well, force is perpendicular to OP. Well, the resultant force always goes towards the centre. But the way I now have my drawing done, perpendicular to OP, there would be no forces. Because if it's going towards the centre, it's purely, the way my picture looks at the moment, it's purely vertical. So forces perpendicular to OP will be 0. So there's good old Bob. I'll have the frictional force going to the left, I'll have a component of the gravitational force going to the right. So I now know mg cos theta minus F is equal to 0. I have an expression for friction. Okay. Now if I go parallel, well, parallel, the resultant force is the circular motion, so the mr omega squared. And if I look at all the ones going vertical, I have the normal force going down and the force due to gravity going down, but the component, mg sine theta, going down in this one would be positive, because we said directed towards the centre would be positive. So I get n plus mg sine theta is mr omega squared. So there's an expression for n. Remember, we're looking for an expression for F divided by n, I think it was, wasn't it? So if I sub that in, there's my expression. The masses end up cancelling, and I get g cos theta on r omega squared minus g sine theta. So this idea of resolving along the bank can be very useful. Because if I want to just find the friction, or I just want to find the normal force, and they're always perpendicular to each other, rather than getting components and solving simultaneously, I can rotate the problem. So if I go back to the bank curve problem, remember there it was, and we had normal force going up, gravitational force going down, friction, well, it could be going in either direction. I've just drawn mine going down for this one. But I could do that same thing. I could rotate the problem. So the normal force now looks like it's going vertically. The frictional force looks like it's going horizontally. But you'll have a component of the gravity now.
No, thank you.
And the resultant force, well, that's going to be rotated as well. So the resultant force, there'll be a component of the resultant force. It allows me to find it very neatly now, because if I just think horizontally and vertically, I can say, well, along the bank, or what looks horizontally, well, the resultant force is the component of mv squared. So I know it's going to be mv squared on r cos theta. And then if I just look at that, well then friction now is totally to the left, and there is no mention of the normal force in there. So I can get a neat expression for friction without having to worry about the normal force. Because remember, friction, normal force, always going to be at right angles to each other. So you can always do it that way. So bingo, there it is. F plus mg sine theta. Rearrange it. There's an expression for friction. And then if I wanted to find an expression for the normal force, I could do the same thing, but perpendicular to the bank, what looks vertical would be mv squared on r sine theta, and there's an expression for the normal force. You see, the other way of doing it is you would have ended up with simultaneous equations, and you have to play with sine squared plus cos squared and get it there. But that is just so much quicker. What I was talking about before, when I said, oh, I hate it when they ask it this way.